Indian Institute of Technology, Kharagpur, and just yeah. And so this is the place. I'm from India, and as Professor Schweiger mentioned, that we have been having a lot of discussions over the last couple of years regarding collaborations, and very recently we have actually started collaborating in a more formal way than before, and we are going to work a lot together on the area of lithium-ion batteries, its testing, and modeling, and things like that. So in IIT, we have been working on lithium-ion batteries as well, especially for hybrid electric vehicle applications. And we have a project with our Indian counterpart, Tata Motors industrial counterpart, and they're building a hybrid electric vehicle, and we are designing the battery, lithium-ion battery pack for that. And of course, we have worked on a couple of other things like two-wheelers and other applications, underwater applications and things like that. And I'm able to show that. I can't show you the hybrid electric vehicle picture because that vehicle hasn't been built yet. And whatever little bit we know from the company, they are not going to share it. They are not allowed us to share it outside. So we'll all have to wait for a public disclosure of that. And of course, our main emphasis is, of course, in building things like BMS. And while working on BMS or battery management systems, we came across a more important aspect, which we call as state of health. Right? And all of us have used cell phones, and we know that if once a cell phone battery becomes old, and you charge it fully, but within maybe half an hour or 1 hour, it goes bad again. So that's because its health is not good anymore, and it has to be discarded. So while a cell phone is not such a critical for the battery life is not such a critical matter, and especially with power banks, etc., we can always boost it up. But if you are driving an electric vehicle and you're out of charge and your battery is not even taking charge and halfway through, then you will be in big trouble. So this state of health is something that we started looking at. And so this lecture today is mainly to discuss our experiences on estimating the state of health of a lithium-ion battery based on whatever measurements are available. So I'll start with some introductions and some definitions, and then I'll describe briefly a concept called particle filters, which is a kind of extension of Kalman filters, because this is a technique which has been used extensively in the literature for state of health estimation. And then I'll show how we have tried to do that using particle filters. And then I'll go to another important way of determining the health of a lithium-ion battery or any other battery for that matter, which is called EIS in short, or Electrochemical Impedance Spectroscopy. And I'll explain what it is and how it can be used for estimating the health. And the major difficulty with these EIS techniques as we know them today is that you have to take the battery out of the car and then have it tested. So what we are trying to do is using some kind of modeling technique which can be extended to develop online methods of estimating the EIS spectra, the spectra that we are going to talk about. And then finally, I'll conclude based on some of our own experiences, sharing that, and some of the facility that we are developing. And of course, I'll conclude after that. So this audience, I guess, is very much aware of batteries. So I'll not go into too much of detail, but just to set the tone of the discussion, we are going to talk about secondary cells, which are rechargeable. And among them, these lithium-ion batteries are the ones which are really finding applications in various areas like, laptops, in cars, in data centers, and, even wrist-worn, blood pressure measurement devices and things like that. Because they are rechargeable and people can use it again and again. And so they are called secondary cells or rechargeable cells. And among them, lithium-ion batteries are the most promising ones as of now. And as far as the electric vehicles are concerned, the almost 40% of the cost of an electric vehicle, especially for pure electric vehicles, I mean, a significant portion can be due to the batteries alone. So the operational cost of a car will actually increase drastically if a battery goes out of service very quickly. So it's very important to increase the length of the life of the battery, and also to monitor it or measure it or estimate it from time to time, so that it's always in good condition, and we have a comfort level that the battery is not going to suddenly go out of order when you are in a difficult place. So batteries are characterized by a very important parameter which is called the state of charge. So state of charge is actually the amount of charge which is present in the battery it's relative to its capacity. So if a battery has certain capacity in terms of charge capacity, in terms of say ampere hour, right? So 100% means it is fully charged, and or it could be 50%, or as I said 31%, and it is typically shown by a symbol like this. So the green part is actually the amount of charge left in the battery. So the state of charge is the percent ratio of the actual charge to the capacity, and it's expressed in percentage. But today we're going to talk more about this parameter which is called the state of health. The state of health is a measure of the current status of a cell in comparison to the point where we started with the battery, right? So when we have a fresh battery, it may be able to store the full capacity. Suppose it has a 20 ampere hour capacity, and we charge it, and it will take up to 20 ampere hour. But as it degrades due to various reasons, its capacity may go down to 19 ampere hour or 15 ampere hour, like that, right? So at some point you have to say that, okay, this is no longer going to be useful for our application. So because a car which was having all new batteries may have a range of 100 miles, and a car which will have a ampere hour rate of 15 ampere hour will probably have 75 miles capacity to run 75 miles, because the overall charge capacity is going down, right? And apart from that, there will also be a state of charge. Now that 15 ampere hour, if it is fully charged, then it will be able to have 15 ampere hour charge. But if it's half charge, then its capacity will become, instead of charge is 50%, then actually it is going to have 7.5 ampere hour. Well, a fresh battery with an SOC of 20 ampere hour will have, and even at 50%, it will have 10 ampere hour of charge stored in that. So as the capacity degrades, the SOC, you need to always have it at the full capacity to even get a 50% of the previous one, right? So we cannot use a capacity of a battery whose state of health is such that its actual capacity has become 70 to 80% of the nominal capacity, the capacity of a fresh model, right? And there are a couple of other definitions. One of them is called the C rate. It is the rate at which we charge or discharge a battery, typically under experimental conditions, because when we actually use a battery in a car, the charging rate or discharging rate depends on the rate at which it is being utilized, right? Or it's the rate at which the charger is charging it, right? Especially in hybrid electric vehicles, that both the charging rate and the discharging rates can be variable. While if it is a pure electric vehicle, especially plug-in type, then during charging, typically we can control the charging rate, but discharging rate, of course, is always depending on the drive cycle. So if it is a full, we say that discharging rate is C/2, if the time taken to completely charge or discharge is 2 hours, right? That is, if it is a certain ampere hour rating, the amount of time it takes is, if you charge it at 2.6 ampere, it will need 1 hour to charge, right? So if the C rate is half of that, so if the current is 1.3 amperes, it will take 2 hours to go up to the same level. So this is called C/2 rate, will require 2 hours to charge. And there is another different definition, especially which is coming to becoming useful for determining the capacity of a battery and especially the state of health. Is called the ampere hour throughput. And this is an interesting quantity in the sense that we take the absolute value of the current that goes into the battery or comes out of the battery, and irrespective of whether it goes in or it comes out, we take the same numerical value, that is, we take the absolute value of that current and then integrate it, right? So it is not really a charge, because charge will be something like 0 to t it dt, right? But here we are taking the absolute value of that, and we call it as the ampere hour throughput or AH value, right? And this one actually decides the usage of the battery. Whenever we use a battery, either we charge or discharge, there are some electrochemical changes within itself. So there is some kind of a degradation. So that degradation will not be captured if we just take the current with its nominal, positive and negative values, because if you are charging a battery with a positive current and again discharging with a negative current and so on, apparently there is no change. You are not causing any change to the battery. But the degradation happens here in the positive part and also in the negative part. So both of them cause degradation. So this ampere hour throughput is a interesting concept in which we basically take the absolute value of this and then we use it as a measure of degradation. And we have started using that to estimate the state of health in a more scientific way. And as I mentioned that there are various reasons for which the battery will degrade. Today, I'm not going to go into the details of this. In fact, these are more electrochemical phenomena because of which this happens. But some of the electrical and aspects are also responsible for that. That if there is a kind of internal short circuit or, as I said, breakdown of electrolyte or formation of, formation of various films and other things in the electrodes, and because of that, the degradation happens, formation of dendrite and things like that. So those are some of the internal factors, and also some external factors which are like abuse, right? So if you have a driver who is very aggressive, it's possible that the battery will degrade faster, right? So we have to be careful about that, and we have to capture that in our your estimation. Otherwise, we'll be going wrong. So overcharge, over discharge, or even mechanical vibrations and shocks, or even the change in ambient temperatures, all these can affect the variation in the degradation of the battery. So now, suppose there is such a situation and the battery capacity falls. So how does it happen? If we plot the capacity of a battery with the increasing number of cycles, there is a number of cycles, it is charged fully and discharge, charge and discharge cycles. So typically, as I said, so real charge discharge doesn't happen like this, especially the discharge, because it depends on the drive conditions. But to start with, we take a notional value that suppose it has been fully charged and discharged, then how would it degrade? And that is typically the kind of experiments we do in the lab, because we try to see the effect of charge, the number of cycles on the capacity of the cell. So if we plot that, we see a degrading, a decreasing trend typically in terms of the total capacity. And there is a point which is typically say 80%, right? And if the capacity falls to 80% from 100%, right? Then we say that is that's the life of the battery. That's the end of life of the battery, TEOL, end of life of the battery. And if you are at a certain point, right? And from that point, whatever is the amount, the time that is available, that will be called as the remaining useful life. The issue is that at this point of time, right? At this point of time, you have to predict, right, how long it is going to last. So what it means is that we have the data available like this. This much of data is available, and this has to be predicted to predict the remaining useful life. So that is the issue here. That is the problem that we have to solve. So this is called the remaining useful life, and how to estimate that. Now, there are different measures of estimating the degradation. One of them is called the capacity fade. That is, as I have explained, that when the nominal the actual capacity becomes 80% of the nominal capacity, that we call as the end of life, right? So this is how the definition. 80% of the nominal capacity, we call this is the end of life, TEOL. This is one aspect. There are other reasons why we need to look at other parameters, because the other important feature is called the power fade. That is, the capacity may be there, but the battery may lose the ability to give a high power, right? And that typically happens when its internal resistance increases, right? So you know that, and all of us know a simple example of a battery which we learned in school, right? A cell, right? A voltage cell. So it has some kind of open circuit voltage and a resistance R, right? So if the R increases, right, the current that you can draw from the battery will go down, right? So this is exactly what happens. So your ability to draw current, right, or the power, in fact, because power is the voltage, the power is going to be voltage into current. So that will come down if current comes down. So that is called power fade, right? So even if your nominal capacity is there, if the resistance increases, and that typically happens because of dendrite formation and loss of lithium and all that. So that actually increases the internal resistance. In fact, these three parameters are not independent, especially power fade and internal resistance are very much related. In fact, in kind of inversely related, because if there is a resistance growth, right, then power will fade, right? So both these are somewhat related, but capacity fade and these other two parameters, they're all important parameters. So they are all sort of considered as a kind of ratio of their nominal values, and the state of health is determined by the ratio of the actual value of the capacity with respect to the nominal value, actual value of resistance with respect to the nominal value, or actual value of the discharging power with respect to the nominal discharge power, right? So this way we can actually compute the various quantity. So there are many approaches. As I said, that particle filter has been used quite extensively in this. And some of the work which have been done are actually with different types of cells, right? Different types of cell chemistries, cell designs, right? Pouch cells and 18650 cells. And to estimate the state of health, we need to model it in some way. And in most cases, these models are empirical, right? And empirical in terms of some of them are linear, some of them are exponential, and things like that. And also, in fact, I'll explain this in detail. Our team, we actually used a fusion of multiple parameters, and we found a much better performance of the system. And so most of them are based on empirical or equivalent circuit models. And the technique used for predicting the state of health is typically the particle filter or its different variants, right? And the model that we developed, as I said, that some of them are functions of ampere hour throughput, temperature, and depth of discharge, especially this work, which is a very interesting work. But more in the past, more conventionally, these are functions of the cycle number. But as I said, that there are certain limitations on the use of cycle number for estimating the state of health. So I will now go into a little bit more detail into the particle filter. And so this is actually a kind of extended version of a Kalman filter. And when we use a Kalman filter, typically we design it to be the noise in it to be a Gaussian noise. But if the noise statistic is not known, right, that is, if it is not non-Gaussian, right, then the problem becomes more difficult. So in that case, what we have to do is that we have to not only estimate the state variables like we do in a Kalman filter, but we also have to estimate the distribution of the noise and other quantities. And because of that, we have to use what is a kind of Bayesian approach, right? As you know that you can refine the estimate using maximum likelihood of Bayesian technique using Bayes rule. So we use not only we estimate the parameters of interest, like suppose we have a state of health parameter, we not only estimate that, but we also estimate the various noise which is there present in the system, right? So how do we do that? So basically what we do is that instead of working with one sample, right, we have a collection of particles, right, a number of particles, and each one of the particles sort of has its own trajectory. Now, many of you may be familiar with particle swarm optimization, right? So when instead of optimizing a single entity, we take a kind of swarm or a collection of particles, right? And we observe their trajectories, right? And then by combining their trajectories and how it's behaving, we actually create a distribution, right? So maybe initially we thought that our distribution is like this, but as we keep going, we actually have a better idea of the distribution, right? And then we know that our estimate is going to be better, right? Of course, I have drawn Gaussian, but it need not be Gaussian either. So to start with, we do not know the distribution. So we assume something. And then what we do is that we then take samples from that distributions, right? And that is called particle resampling, right? And then by resampling, we actually again reconstruct new set of particles, and then we let them move, and then that way we keep repeating the estimating. And all those particles, whenever we try to combine, we use also a weighting factor so that we give appropriate weightage to the particles, right? So that is an extension. So you can say it's a number of Kalman filters which are operating in parallel with different different particles, and we actually are trying to look at not only that the individual trajectories but also their collection or the whole distribution. So that is the essence of a particle filter. So we have used these particle filters initially for capacity degradation, to estimate the capacity degradation, and then resistance degradation, and then I'll show how we have done a fusion of both of them, right? And so typically the capacity degradation uses a mixture of two Gaussian models. So as I said that it need not be pure Gaussian, so it's a mixture of two Gaussian components, right? And so particle filter can be used to represent this type of non-Gaussian. I mean, two Gaussian is not a pure Gaussian model, so it's a mixture of two Gaussian models. So we tried that model, right? And then we did experiment to measure the battery capacity after every cycle, right? And and then at certain point of time we have to predict the future. So there at that time we actually update the parameters using the particle filter, and then check when when it crosses the failure threshold, right? And then based on that we estimate the remaining useful life. So to give you an example, it's like this. So we have at some point, so as I was saying that at some point of time we will get some data, right? And based on that we have to actually predict the future, right? So this is the data and this part is the prediction, right? So if we have got very little data, then the prediction will not be very accurate, right? But still it will be, we can do something if we have a reasonable amount of data. So if we have say 30 samples, we make a prediction, right? So at the point k equal to 30, we are making a prediction. And this is, and we have already got the data. Only thing is that we are not using it, and we are trying to see at what time it is failing. So we know that it failed after 181 cycles. So this remains intact, right? And our prediction says that it will fail after say 178 cycles, right? And then we have actually, and then we, as we said, that we are also estimating the distribution. So this is how the predicted distribution looks like, right? And of course, it will have its mean, it will have its variance, and you can plot that. And then we saw that using this, we got a certain standard deviation, right? So at different points. And in fact, you will see that the standard deviation falls as we increase the time period, right? So the more data that we have got, now we are predicting based on much more data, 100 data points, right? In this case, we are actually we are at the end point, right? No, there is hardly any prediction, right? So this distribution, the variance decreases, right? So this decreases from as we get more and more sample points. So this is one method of estimating the state of health by checking the capacity degradation. Now, internal resistance is also a parameter, and typically we use a polynomial type of distribution or variation for this. And we actually did the EIS test, which I'm going to talk about a little later, to estimate the impedance, right? And the resistance part of the impedance is actually the internal resistance. So again, we use the same structure, and I don't need to go into it. Basically, we are using the same type of prediction for resistance, right? So in the same way, we find that we have at different points of time, we estimate the point of failure or estimate the remaining useful life. And again, here you can see the standard deviation reduces as we go closer and closer to the point of failure, right? And the prediction error also reduces as we go on. And next, what we did is that we failed, people will also have a difficulty in figuring out whether the battery degradation is because we may be getting two different estimates from the capacity degradation and the resistance degradation. So we thought, why not we fuse both the estimations together and get one quantity of the remaining useful life. So we actually fused the two things together. So there is a capacity degradation model and there is an internal resistance degradation model, right? Or growth model. And we applied the same technique, and then we predicted the RUL, remaining useful life. And we found that this gives you us a much better prediction. In fact, you will see that, all of them actually, they predicted very close to each other, and the standard deviations are much less, right? So you can say these are 4.44, while in earlier cases, this was something like 13 or 7 or something like that. So the standard deviation, you can also see from these pictures that the distributions are narrower, right? So that tells us that the standard deviation is actually reducing. So this is one interesting work that we did. And more recently, we are working on ampere hour throughput. So our results are still preliminary, but one thing we're trying to do is to use more aggressive charging and discharging, operating at 2C rates, and see whether we can actually get a good prediction. So our preliminary results are reasonably fine, right? As you can see. But we have not done still. In fact, we got stuck with our COVID lockdown. So a lot of experimentation is planned, which are yet to be done. But this is something which we have started. And another thing we are trying is that we are working on indirect health indicators, right? So there are some other parameters like the cutoff voltages, right? Or the discharge voltages, or the maximum temperature, or the time taken to reach the maximum temperature. These will affect the these are also indirect indication of the degradation of a battery. So people have worked on it, and we have also started working on this various indirect health indicators. And we are also getting, we have not completed our work again on this, but you can see the similar trend which are observed using these indirect health indicators. And these are a little bit less computation intensive. So we are looking at it because we would like to really implement some of these RUL estimation techniques on board. So we're trying to see whether we can get improved estimation and with reduced amount of computations. So you can see that we are actually getting, some kind of drifts at the moment, right? We are trying to improve that. So once we are done, we are hopeful that we'll be getting much better performance. So with this, I would like to move on to the other topic, which is the electrochemical impedance spectroscopy, or the EIS, right? So this is the method to estimate the impedance spectrum of a battery. So modeling of a battery is very complex. In fact, we really need to have partial differential equations to express the operations of a battery. But we often use a simplified equivalent circuit models. But they have certain limitations, especially the typical resistance capacitance models that we use. So we have started looking at some alternative models which are linear, but have other features, and which are called fractional order models. And we have got excellent results using that. So I'll share with you some of our experiences on that. So EIS will help us basically to estimate the degradation in a cell in a very meaningful fashion, especially in a very in a demonstrable fashion. And so basically EIS is basically the impedance, the ratio of the voltage and the current in the frequency domain. So at different values of frequency, if we sort of inject a current into the cell or the battery, or draw a current from the battery, then there will be a change in the terminal voltage, right? So if we take the ratio of the voltage to the current, right, at different frequencies, then we will be getting this so-called electrochemical impedance spectrum, right? So this will be a complex number. So it will have a real part and it will have an imaginary part. Or you can also say magnitude and phase, right? So typically it is plotted in 2 dimension, and then one versus the real versus the imaginary part, and we get very interesting patterns. And we do the experiment at different frequencies, and especially at very, very low frequencies. And there is a reason why we do that, because that actually accentuates the degradation, right? So briefly, this is a very reliable method, and in fact you can say it is a kind of gold standard, especially when you do offline, by taking all the precautions, like allowing the cell to settle before you take the measurements and things like that. And so once you have the impedance, you can do a lot of things, like even balancing methods, designing balancing methods and things like that. But as I said, there are also some limitations, and and these are all practical limitations, like it takes time and it takes expense and it takes a lot of operations, like removal of the battery from the car, right? So if you're looking for onboard methods, then this is not going to be helpful. So what can we do? Can we try to estimate that in a different way? So that's what we are trying to look at. And so as I was saying, that you have the impedance Z, right? So the real part ZR versus the impedance, the imaginary part with the minus sign typically. If we plot it, we'll get a pattern like this, right? And as you can see that, high frequencies are here, 1 megahertz, 1 kilohertz could be here, and the lower frequencies, millihertz and all, they will be here. So it is a very interesting pattern, right? And you will see that integer order models will not be able to fit this kind of pattern. And that will give us the motivation for using a fractional order model. So again, this is the same thing, our impedance is defined like this. So now what is the interesting thing about this EIS is that if we take a fresh battery, right? So suppose that has a this EIS number 1. After some aging, this will change to this number 2. After some more aging, it will go to number 3, right? And so you can see, so if we call this to be the tail of the EIS, so tail actually gets moves to the right, right? And what happens also, if we actually can define a resistance called critical resistance, right? And that resistance also increases as the cell ages. So this is very, if we can capture this behavior, then we can very easily determine the state of health of a battery. Now this is a well-known technique. The only problem is that this is not possible to do it online, right? And as I said, that this type of behavior cannot be explained by typical RC circuits. And what we need are extra elements, which are typically called, fractional order elements, or they are also called Warburg elements, right? Sorry. Yeah, fractional order. Yeah, so fractional order elements, right? And they are also called Warburg elements. So we need to insert these, and they make the modeling much more complicated. And so, but there is a way to handle that. So as I said that, typically what we have are integer order models, the conventional ones, and what we are looking at are fractional order models. Let me skip this because I'll explain this in a different slide as well. But in terms of behavior, basically, the transfer functions of an integer order system, which are all well known. But for fractional order models, you'll have factors like s to the power 0.5 and things like that. So their responses will be atypical. They will not be like a first order system that we are so much familiar with, right? Right. So both are first order systems, but with a half fractional thing, there is a difference in the response, the time response, right? Similarly, there is a difference in the frequency response as well, right? So although they are both first order, you can see that the middle frequency behavior is different. Mid frequency behavior is not the same, right? So as I said, so we need to set up a model where these fractional order elements will be captured, right? So what we did is that instead of using pure capacitors, we use what is called as a constant phase element, right? A constant phase element, right, will have a fractional order, right? And by using that, it's a kind of it's a capacitor with a different characteristics. In fact, it's actually, if we have a pure capacitor, then we can write it as I equal to C dV dt. But instead of a pure capacitor, we have a C times d alpha V dt alpha, right? Where alpha lies between 0 and 1, and typically alpha will be 0.5. And using this, we can actually set up the whole set of equations, right? Including the state space models, right? And then we can use this to estimate represent the this complex model. Relatively more complex model, which is called as a fractional order model. So we can then actually put it in the form of a standard, Kalman filter and things like that, and the regression and estimation of the parameters, states, and everything like that. So only difference is that typically we use normal state variable filters. In this case, we have to use so-called fractional state variable filters. If anybody is interested, later on I can share or I can refer you to some of the publications that we have about how to design those. But basically, apart from that, we also need to design what is called as a fractional order Kalman filter. Right? So these are the couple of changes. Once we do that, I mean, of course, it's easy to say that, but no, when you try to implement it, it creates a lot of computational difficulties. But that's a separate issue. But it's in principle, it is possible to do it. And using this, what the results that we get are really fantastic in the sense that we have done experimental work and then the modeling, and you can see there is a very close match, right? And I need not go into the details of the time variations, right? But as we saw that, as from 100th first cycle to 100th cycle or 120th cycle, there will be some variations, and experimental as well as our models, they are able to track the variations. Of course, the exact shapes are still not the same, but at least the pattern is visible, right? And especially if we really look at the aging, right? So you can see that how the aging is being captured using the fractional order elements, right? These are the experimental data, and these are the fractional order elements. You can see the patterns are captured reasonably well. While if you take a integer order model, so-called the conventional models, then you can probably get only the this kind of elliptical part, not the tail, right? So these models don't have any tails, right? So that's the difficulty with the integer order models, but which is very well captured using the fractional order model. And these are some of the time domain expressions. You can see that they are all able to predict pretty well. And with this, let me come to a brief description of what we are doing in some of the experimental facility at our place. And as I mentioned that we work on the BMS, the battery management systems, and probably you are all familiar with the functions of a battery management systems, which are on sensing, monitoring, and balancing of the cell. And this will have, when you try to build it, it will have communication and protection. All these aspects are there. So this is a typical, and architecturally, this is a standard BMS architecture. Of course, we have customized it for our requirement based on our battery pack and our master slave configurations. And we have built up, we have got all the hardware cards developed. And there is our experimental facility for building active cell balancers and all that we have in our institute. But more importantly, what we want to design, and we have started, I would not say that we have already completed this design. Basically, we would like to convert our BMS into a battery health management system, which will have RUL estimation, capacity degradation, power fading estimation, battery online impedance measurement estimation, and also we'll try to build things on the ampere hour throughput and other indirect health indicators. So apart from some of the small systems that we have built and our typical boards and all, we are actually working on this particular battery for the hybrid electric vehicles with our industry partner Tata Motors. And this work is going on in full swing. Of course, as usual, the experimental work is a little bit stuck, but as the design and other things happening. So this is how our battery pack looks like, our current design. And of course, it may change, and it will have air cooling facility. And our all these cards, etc., will also be packaged, in compact fashion in the same enclosure. And so this is the typical, about 2000 watt-hour battery pack that we are trying to build using pouch cells. So the design and test facilities are there. So we do, we're trying to estimate the thermal characteristics of the batteries. And this area also, as Professor Schweiger mentioned, we are collaborating. We have started collaborating on this area. And we've also got the various other experimental facilities like thermal chamber, the pack cyclers, cell cyclers, and many of them are freshly arrived and just gathering dust in the current conditions. But we are hopeful that maybe from the January onwards, we'll be able to start using them once again. So with this, let me conclude. And I've already probably talked about all these points, but still let me summarize. So as I said, that monitoring the health of batteries is very important, especially for EVs, right? And the range and the acceleration ability. So vehicle range will come down if there is a capacity degradation. Acceleration ability will come down if you have a power fading or the resistance increase of the increase in the internal resistance. And so a lot of studies on estimating the state of health are based on full charge discharge cycling, right? And which are difficult to extrapolate to regular usage, because there will be a drive cycle data, and that people will not be really charging or discharging fully, right? And because they have to actually run the car rather than look at its life at every point of time. And the EIS is a very good method. So, but then it's not online as of now, and some efforts are being made, and we are also trying in our own way. And so which some of the methods which gave us good success was this kind of things, fractional order modeling, but it also has limitations, as I said, because there are a lot of computational issues, right? And finally, this is our goal, right? And still people don't build this kind of systems. This type of systems like health management systems are very common in aerospace industry, and probably also in high power industries like the rails, right? Electric trains and all. But in cars, it is still not become popular, especially because batteries are also new, new technology. But it's going to be more prominent as we have more and more EVs and HEVs on the road. With this, let me just almost conclude with a list of some of our own papers and some very key papers from the literature that we have followed. And I'll be happy to share all the list and the presentation. So with this, let me conclude, and feel free to ask me any questions. Thank you.
Thank you very much for a very interesting presentation. And we have right now one question in the text